Well, as you can see, we've got the pre-Chapter 8 review problems, and this is not necessarily going to be an instructional video. It's more just to give you the answers and a couple explanations for a few of the problems. So anyway, I want to just go ahead and show you the answers, pause the video so you can check yours, and if you haven't done the problems yet, then make sure you don't watch the video at all until you finish all 42 problems. And to give you an idea, I don't know if you timed yourself or not, but I think between 15 and 30 minutes is reasonable. Probably more closer to the 15, the better. I think if you're faster than 15 minutes, then you are, and you've gotten them all right, then that's really, really fast. So if you want to challenge yourself, and by all means go ahead and do that. Now the reason why I'm not going to be giving you necessarily an instructional video on these, on this worksheet, is because these are all obviously review problems, and you should already know how to do them. Now you might not remember how to do them all, but they all come from previous chapters. In fact, some of them come from last year in Pre-Calc Honors when we dealt with their unit circle. But I want to stress how important it is that you do know how to do all of these problems, all 42 of them, because it will really help you a lot to have all of these concepts understood and clear in your mind before you start Chapter 8. Chapter 8 will first of all deal with limits, and then get into functions growing faster than others, and then we get into what we call indefinite integrals, or I should say improper integrals, and the concepts are actually pretty easy to understand in Chapter 8, but what trips most students up when they don't understand something is not the new stuff. It's, as I've probably been saying all year long, it's the old stuff. So, that being said, here we go. So you should have already seen these. I'm going to scroll on down here so you can check out, so you can check your answers. So let's see, numbers 8 through 12. All right, here I highlighted a couple of these. I highlighted the ones I thought were the hardest, or at least the ones that I hear the most questions on, and that the students get wrong the most. On the way, all the way down there to number 12. Okay, and then numbers 13 through, what can we fit in here? 13 through 16. For number 13, just a quick heads up on that one. When x is approaching infinity, then we take any expression that has an x in it and we say, well, where is that expression going? It's like here for number 13, e to the 1 over x. Well, if x is getting really, really big, then the fraction 1 over x is getting really, really small. In fact, the fraction approaches 0, so you can replace that fraction as x is approaching infinity to figure out what the limit is. You can replace the fraction with 0, and same over here with 1 over x. 1 over x is going to 0, so you replace that fraction with 0. So if you hear any noise in the background, my bad timing to do these videos, but the gardener's here cleaning off the courtyard. Anyway, that's what that is. Hopefully it's not too distracting for you. It's distracting me a little bit. So anyway, on down to number 17. And number 17 I highlighted because this is typically a pretty tough limit for many students if they don't remember what the tangent function looks like as far as the graph goes. So if you graph it, it's really easy. You look at pi over 2, there's an asymptote there. When you approach pi over 2 from the left, no, did I make a mistake on this one? I think I did. So pi over 2 is right there. There's an asymptote, and it actually goes up to positive infinity. So let me correct that right now. It goes to positive infinity. So when you approach pi over 2 from the left, the graph of the tangent goes up to positive infinity. So anyway, there you go. Maybe you caught me on that before I caught myself. 18 through 21. And we can see just a quick reminder that when x is approaching a real number, then the first thing you should do is replace x with that real number and see what the value is. And if it's a real number, then you're done. Okay? And on the way down to number 21, 21 is easier when you understand what the graph looks like as well. So the graph of the secant of x approaches an asymptote when x is approaching pi over 2 from the left. The values of the secant of x approach positive infinity, and that is just to the left of that asymptote. Okay, and then this should go pretty quickly. 22, 23, and 25. Just replace x with whatever x is approaching, and the ln of x, when you look at the graph of the ln of x, you see that as x is approaching 0 from the right, the y values are getting smaller and smaller down to negative infinity. Same thing here with 0 from the right of 1 over x. We know the graph of that from the right hand side as x is approaching 0 from the right, the y values are getting really, really big up to positive infinity. Okay? And then 24 and 26, 0 and 0. And then the unit circle values, it's really, really frustrating when I see students do all of this work on the Chapter 8 material, and they get all the way down to sine of pi over 2, and they put something like 0 there instead of 1. Same with cosine of pi over 2. I think that the one mistake students make the most probably is a cosine of 0, and they put 0 in there. That happens when you're not thinking, when you're not concentrating on the little details. So all the way down to number 33, and then all the way up to number 34, down to 36. And just when you have an equation in log form and you need to get at that variable, you want to convert it to exponential. Okay, 36 and 37. I put these on here because these are the ones that students ask a lot of questions on. If you were to graph y equals ln of x squared, you would see that it hits 3 two times in 2 places. But if you were to graph y equals 2 ln of x, it only hits 3 at 1 place, because this function here has a domain of all real numbers except for 0. This function here, even though you could put that 2 from the position it's in now to the exponent position, it's not in the exponent position to begin with, so therefore these are 2 different functions. They have the same exact values to the right of 0, but only the one in number 36 has values to the left of 0. In other words, you can replace x with any values to the left of 0. So you can see that there's a plus or minus in front of the e for number 36, and there's only the positive value for e in number 37. Okay? And then 38, ln of x, 1 over x, 40, 41, and 42. When I graph the secant of x, I first graph the cosine of x because the secant is the reciprocal. So when I see where the cosine is, I know that the secant is just, they meet at 1. Anytime that the cosine is 1, the secant is also 1. Same with over here, where anytime the cosine is -1, the secant would also be -1. And so we see the graph of the secant, tangent, and cosecant. So if you still have questions, I would urge you to try to figure out the answers to your questions on your own, but I'm certainly able to help you. But it really does help when you do the research on your own, then you'll be more inclined to remember what you didn't remember the first time. So hope that was helpful, and we'll see you in the next video.